The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, today we begin a topic dear to my heart. It's a problem that's still pretty open, but I've worked on a lot. Dynamic optimality. The central question here is there one binary search tree that's at least as good as all other binary search trees? Is there one binary search tree to rule them all? It's kind of a fundamental question. It goes back to the 80s. It's in particular splay trees, which you have probably seen before. We'll review them briefly here. And there's a lot of technology built up, which we'll talk about this lecture and next lecture, about how to tackle this problem. It's still active area of research. So before I get to, well, the central question here is there one best binary search tree? It's a natural question because we use binary search trees all the time. Already in this class, probably every lecture we've used a binary search tree for something. And we all know how to do order log n, balanced binary search trees. And the question becomes, is this the best you can do? To make this more formal of a problem, I want to define binary search tree as a model of computation. Okay, we've talked about pointer machine model. Binary search tree model is a more restricted version of pointer machine. So it's less than pointer machine. Just so it's clear what the name of this game is, we require the data to be stored in a binary search tree as its keys. And then we allow basic operations. Let me make sure I get the right list. You can follow pointers, and we're going to assume our BST has left child pointers, right child pointers, and parent pointers. You can do each of these in constant time. And then the interesting thing you can do is rotate a node and its parent. Okay, so I'm sure you've seen rotations before. If this is my node x and I do rotate x, that's going to be my definition of rotation. X moves to the root. It's, in this case, because x is to the right of its parent, it remains now to the right of its what now becomes its child. These subtrees come along for the ride. This preserves the binary search tree property, and you could get back by rotating y. Okay, by this definition of rotate, we don't need to distinguish between left and right rotations. We always name the child, and its parent is well defined. That's who we rotate with. So it's just flipping this edge. So these are the operations you can do, and in this model, really the only thing you can do is a search. Suppose I want to search for a key. The model is to do a search. I start at the root of the tree, of the binary search tree. I can do these walks, I can do rotations, and I must visit, if I'm going to search for x, must visit the node with key equal to x. And we're going to assume throughout these lectures that searches are always successful. You're only searching for keys that are in the tree. Doesn't make that much of a difference. If you're searching for keys that are not in the tree, think of it as searching for the predecessor or the successor. Not a big deal. And so for simplicity, we're just going to assume successful searches. We're also going to assume no insertions and deletions in this model, because they just make problem a little messier. Some papers have considered insertions and deletions, and to the large extent, things just work. So we're going to focus on searches. Searches is interesting enough for this problem. Suppose I have n items. Now the model's clear. I store them in a binary search tree. These are the only things I'm allowed to do. Could I imagine beating log n? Well, no, in the worst case. This is best possible in the worst case. Why? Because your tree has to have depth at least log n if you're going to store n things in it and it's binary. So your adversary could always just look at your tree and say, oh, I'm going to pick anybody who's at log n depth or lower. And if you're going to start at the root and walk left and right to get there, you're going to have to pay log n time every single operation. So actually, there's a lot of sequences. In fact, most sequences, you take an average sequence, this will be the case. But we'll see formal ways to prove that next class. But easy adversary argument tells you you need to go down log n in the worst case. But that's the worst case. The name of the game in dynamic optimality is to consider every case separately and do as well as you can all the time. In general, the answer to this question, is log n best possible, depends on the access sequence. Depends on what you're searching for. So let's say to make things a little clean, let's assume that the keys we're storing are the numbers, integers 1 up to n. So in particular, there's n of them. And really, we just care about their order. So I'm going to relabel them to be 1 up to n. And say we search for x1 first, then we search for x2, and so on up to xm. So these indices are time, basically. Over time, and you can plot this if you like. Here's time. Here's space. So at the first time unit, we search at x1, then some other place, then some other place. We can have repeats, whatever. Okay. Some search sequences are going to be slow. They're going to require log n time per access. In particular, if the adversary chooses xi to be the deepest node in the tree repeatedly. But some search sequences are going to be fast. Any suggestions, if you don't have the notes in front of you, of access sequences that we can do in less than log n time per operation, let's say constant? There's a lot of possible answers, I think. Yeah?
N divided by 2.
N divided by 2. What do you mean?
Like, it's going to be the median.
Oh, if you're searching for the median in a perfectly balanced tree? Yeah. That's true. So if you're always searching for the root of the tree in particular, that's going to be good. That's hard to, that depends on the tree though. I'd like a particular access sequence that I can always serve as well with some tree.
In order walk.
In order walk. Yeah, good. So this is, has a name. Sequential access property. If you want to access the elements in order, so 1 through n, this should only cost constant amortized. Because for any tree, you can do an in-order walk in linear time. And so per search, if you're careful about how you do this, now this is not totally obvious in the model that I've set up, because I said search always starts at the root. If you let your search start where you left off, then you can definitely do this. It turns out you can assume this or not, it doesn't make a difference. It's maybe a fun exercise, but if you can essentially reroute the tree to be wherever you left off. I'm not going to prove that here. Okay, but in particular, some trees have this property. Some don't. I mean, if you use a red-black tree and you search for 1, then search for 2, then search for n, you're not going to get constant amortized because it doesn't realize this is happening. But if you're clever, of course, this can be achieved. Easy way to see how to achieve it is this is your binary search tree. You access 1, then you do a rotation with the right child of 1. So then you have this binary search tree, and then you access 2, and then you do a rotation. This is basically a way to make a deck. You know, simulate a linked list in a binary search tree. Okay, so it definitely can be done by some binary search tree. A stronger version of the sequential access property, a little more interesting, is dynamic finger property. This is something that should hold for every access sequence, and it gives you a measure of how expensive an access sequence is. So we're doing x1, x2 up to xm, and we say if we measure the key distance between our current access xi and the previous access xi minus 1, if that equals k, then ideally we should be able to do log k amortized per operation. So in the worst case, this is going to be log n. But if I look at my space-time diagram here, for example, if I do sequential access, then this number is always 1, and so I get constant time. If I do something like this, where my spatial distance is not changing too much, and this is the reason I numbered the keys like this. What I really mean is in the sorted order of the keys, how do the ranks differ? But if I number the keys 1 through n, that's just their absolute difference. So anything like this, dynamic finger property tells you you're doing well. Dynamic finger property can be achieved by a binary search tree, but it's quite difficult, as you might imagine. Or it's difficult, let's say, not necessarily super hard. If you don't need to do it in a binary search tree model, an easy way to do it is with what's called a level linked tree. So a level linked tree looks like this, and I add pointers between adjacent nodes in the same level. This is a pointer machine data structure. It's not a binary search tree, because binary search trees we're only allowed to do walk left, walk right, walk parent. But it's an easy way to do dynamic finger. You start from somewhere, you basically walk up to the right level, move over, walk back down, and you can do a search for xi from xi minus 1 relatively quickly. It turns out this can be simulated by a binary search tree, but we won't go into it here. Lots of fun puzzles here. Let's move on to some more bounds. Or properties. So next property is called the entropy property, or entropy bound. And it says if key k appears p sub k fraction of the time, then I'd like to achieve a bound of entropy pk log 1 over pk per operation. This is everything here today will be amortized. If you haven't seen entropy, that's the definition. It's the entropy of this distribution. We're thinking of these as probabilities, although they're not really probabilities. They're because this is over a particular sample. We have this sequence x1 to xn. There's no randomness here, but we just measure what is the fraction, what is sort of the observed probability for each of these xi's, and then just say what is the What is the entropy of that distribution? In the worst case, it's log n. If, say, everybody's equally likely, everyone's accessed once, or the same number of times. But if it's highly skewed, like if only one element is accessed, the entropy will be constant. Or if a small number of elements are accessed, the entropy will be constant. So this can be achieved. And in fact, if you disallow rotations, so if I change the model to forbid rotations, all I get to do is set up some binary search tree, and then I have to walk left, walk right, walk parent from in that binary search tree to do this. So if I get to see the xi's, then I get to build a binary search tree, one binary search tree. This is what's called the static optimal, when you're not allowed to change the tree as you're doing searches. Entropy is the best bound you can get. And roughly speaking, key k appears at height or depth log 1 over pk in the tree, maybe plus 1. And you can show there's always a tree where every node ends up at depth log 1 over pk. Again, not hard, but we won't do it here. OK. Related property, it's called the working set property. It's a little bit harder to state. For each search we do, xi, we're going to see when that's some key. When was the last time that key was accessed? So in our space-time diagram, we have some access at time I. We want to look backwards in time to the last time that key was accessed. Say that was some other time j. And in this interval, we want to know how many distinct keys were accessed. So it's at most I minus j, but maybe there were some repeated accesses. We only count those as 1. So how many different keys were accessed during that time interval? Claim is we only have to pay log of that. So what this means, what this implies is, in particular, if you're only accessing, say, k different elements at all, and you ignore all the other elements, then you'll only pay log k per operation. That's why it's sort of a working set. If you're focusing your attention on k elements for a while, you only pay log k. But in general, for any access sequence, you can compute what is the working set cost, which is you sum over all the i's of log ti. That is your total cost for the access sequence. Divide by n, that's the amortized cost. OK? It's another nice property. Not so obvious is that working set implies the entropy bound. So this is a stronger property. I guess dynamic finger implies sequential access. But there's no relation between working set and dynamic finger. In fact, they're kind of transposes of each other. Working set is about if you access a key that was accessed recently, then it's fast. Dynamic finger is saying if you access a key that is close in space to the previous access. So here we're looking at a key, and basically in the very previous time step, we're looking at how far away it was vertically. Here we're looking at how far away it was horizontally. So they're almost duals of each other. Be nice if you could have one property that included both dynamic finger and working set. I should mention, again, this is not obvious how to do it with a binary search tree, but it can be done. Leave it at that. We'll see eventually some trees that have it. For now, I just want to cover what are the conceivable goals we should aim for. Right, log n is too easy, so we need more challenging goals. So the next property that was introduced, we're getting into more recent territory, 2001. It's called the unified property, natural name, and it tries to unify dynamic finger with working set. And the rough idea is that if you access a key that was that is close in space to a key that was accessed recently in time, then your access should be fast. So here's the formal statement. So here's the unified bound. Let's draw a picture. So here we're accessing xi time I, j, change of notation, time j. We want to evaluate the cost of xj. And we're basically going to look in, I guess one way to think of it is this cone. 90-degree cone where these are 45-degree angles. And if there's something, look at the first thing that you hit in that cone. Is that the right way to think of it? Maybe not. It's like you're growing a box. This is probably more accurate. And you find the first key that you hit in the box. It's a little more subtle than that because we're only counting distinct keys. But let's say you find this key. And this key is good because its temporal distance, this is time, is only this big. Its spatial distance is only this big. What we're going to pay is log of the sum of the spatial distance and the temporal distance. And temporal distance is measured as the number of distinct keys accessed in this time interval. So as long as there is some key in the recent past that is close in space, you take the min over all such keys. Magically, a unified structure has to find what is the most recent close item and search from there and achieve log of that. There's a +2 just to make sure if these things are 0, you still get a constant. You always have to pay constant time. Okay, so that's the unified property. Fairly natural generalization of dynamic finger and working set. I mean, you could change this plus to a product or a max. Doesn't make a difference. Yeah. Sadly, we don't know whether there is any binary search tree that achieves the unified property. What we know is that this can be done, this property can be achieved by a pointer machine data structure, which is more powerful than a binary search tree. But we don't know whether it's possible to achieve by a binary search tree. Best bound so far is that you can achieve this bound plus log n. So as long as this never gets too small, as long as this quantity never gets smaller than log n, then this thing will be log n and it's fine. But in particular, if this is constant, then it's only achieving log n. So it's not, there's an additive log n per operation loss. That's the best binary search, unified binary search tree known. Okay, this is all good. And this is sort of where the, what we call analytic bounds here ends. There are various attempts to, in general, we want to characterize what is the optimal thing we could hope for. When can we do better than log n? These are all specific cases where we can do better than log n, but it's not a complete characterization. There are sequences that have large unified bound, but have no, yet they can be accessed more quickly by the optimal binary search tree. And so while it'd be nice to characterize with some clean algebraic whatever, most of the work beyond what I've told you about here is just trying to figure out what opt is. Instead of trying to write it down, try to compute it. Instead of trying to define something that happens to match the optimal, let's just go for optimal. And this is the notion of dynamic optimality. And in modern terminology, this would be called constant competitive. But the paper that introduced dynamic optimality preceded competitive analysis, so it has another name. What we'd like is that the total cost of all your accesses, so this is like amortized cost, is within a constant factor of the optimal. What's the optimal? This is the over all binary search trees. I mean, to be precise, I should talk about binary search tree algorithms, meaning you specify somehow how to do a search, and it may involve rotations and walks. So, it could be red-black tree, could be an AVL tree, could be a BB alpha tree, anything that can be implemented in this way. Those are all kind of boring. More sophisticated is something like a splay tree. Ideally, you take the min over all binary search tree algorithms. The cost of that algorithm on that access sequence X, and you want the total cost of your algorithm on X to be within a constant factor of the optimal algorithm on X. X is a vector. So this is what you call the offline optimal, because here you basically get to choose the binary search tree algorithm to be customized to X. And yet somehow you want to achieve dynamic optimality. Open question. Is this possible? And of course, we're only interested in online solutions. So you want to build a binary search tree that doesn't know the future, doesn't know what accesses are to come, but it has to be within a constant factor of the offline solution that does know. We don't know whether this is possible. Another interesting question is whether it's possible for a pointer machine. Because, say, for the unified property, we know how to get it for a pointer machine. And there's two versions of this question. You can consider, is there a pointer machine that matches the optimal binary search tree? Or you could ask, is there a pointer machine that matches the optimal pointer machine? That's a little less defined, although I have some ideas on how to define that problem. Maybe we'll work on it. But all versions of this problem are open, basically. So this may seem rather depressing. What else am I going to do for a lecture and a half? But actually, there's a lot of study of this problem. And we do know some good things. For example, we can get log, n competitive. So not within a constant factor, but we can get within a log n factor of the optimal. So that's pretty good. An easy result is to get log n competitive. Any balanced binary search tree is log n competitive, because best case you could hope for is constant. The worst case you can hope for is log n. So we're always within the log factor. But we can do exponentially better. We'll do that next class. Before we go there, I want to tell you about two binary search trees that we conjecture are dynamically optimal, but we can't prove it. So first one, the classic one, is splay trees. I don't want to spend too much time on splay trees, but just to let you know what they are, if you don't already know. If you want to search for x, you search for x. You do a binary search for x in the tree. You locate x, and then splay trees always move x to the root. So this is what we call a self-adjusting tree. It changes the structure of the tree as you do searches, not just when you're doing updates. And there are two cases. If you look at x and its parent and its grandparent, if they're oriented the same way, so here it's two left pointers, could be two right pointers, then you flip them. So we rotate y and then rotate x. So it's in this model. And we get x, y, z in the other order. pretty much only one way to move x to the root in that picture. Then the other case is the zigzag case, y, w, x. So here the two parent pointers are in different directions. One's left, one's right. There's a symmetric picture. In this case, we rotate in the other order. So we rotate x, and then we rotate y. And in that case, you get, looks nice, x, w, y, and the subtrees hanging off. I'm not labeling the subtrees, but they have to be labeled in the same order, left to right. Okay, this is splay trees. You do this for x. X is the thing you search for. Now x is up here. Then you repeat. You look at its two parents. It's one of these two cases. You do the appropriate two rotations until x is either the root, and you're done, or it's one child from the root, and then you do one rotation to make it the root. Seems simple enough. It's slightly more sophisticated than an algorithm known as move to root, which is just rotate x, rotate x, rotate x, which would eventually propagate it up. Move to root is a really bad algorithm. You can show it can be a factor of square root of n. It can be square root of n per operation if you're unlucky. Splay trees are always at most log n amortized per operation, although that's not at all obvious. Rough intuition is if you look at the path, the root to x path, half of the nodes, at most half of the nodes go down when you splay. So why is that? Here, see, y stays at the same level. Z goes down, but x goes up. Here, w stays at the same level. X goes up, y goes down by 1. X goes up by 2. So you might call that a net improvement. But in general, you don't mess up the path too much. Half the items stay where they are. And so it's something like you're bisecting. If you repeatedly search for x, well, not repeatedly searching for x, but if you repeatedly search for things on that path, you're kind of cutting the path in half repeatedly. So kind of logarithmic. That's a very vague argument. And in advanced algorithms, it's proved why this is log n amortized. Question? Rotate x, rotate x. I think you're right. Yeah, y would go somewhere else. Thanks. Yeah, so here it looks like move to root. Here it doesn't. Good. And there's lots of things known about splay trees. So for example, they satisfy the sequential access property. There's an entire paper, Combinatorica 1985, Tarjan, I believe, proving splay trees have the sequential access property. Not at all obvious, but it's true. They have the working set property, and therefore they have the entropy property. That's in the original splay tree paper. It's not that hard to prove. Once you prove log n, a little bit more effort, you can prove the working set property. Won't do it here. It's a cool amortization. Splay trees also have the dynamic finger property. This is a series of 2 papers over 100 pages long. Very difficult to prove. In general, splay trees are hard to work with because it's hard to keep track of what's going on. You can define potential functions, and that will prove this, and with a lot of effort it will prove this. We don't know whether splay trees satisfy the unified property, and more to the point, we don't know whether splay trees are dynamically optimal. This is the big question, and in the original splay tree paper, it asked this question: are splay trees dynamically optimal? It's still open. I wish I knew the answer, but we don't. So what the rest of today's lecture is going to be about is a geometric view, which I've kind of been hinting at with this picture, but there's more to it than just plot the points of searches. There's a way not only to see what the searches are, but to see what the binary search tree algorithm is. So at this point, binary search tree algorithms are kind of abstract. I mean, we've kind of drawn pictures and how to do specific cases. You know how red-black trees or something work. But it's complicated to write down one of these algorithms. How would we think about all of them? How would we think about the optimal one? Turns out there's a geometric view in which it's actually very easy to see what the algorithm is, but it takes a little bit of work to prove that it's the right thing. And it suggests a totally obvious offline optimal algorithm, which we don't know is optimal, but we think is offline optimal. It's like the obvious thing to do, which we'll get to. And we can actually make it online. So this gives us a binary search tree that is so obviously optimal, whereas splay trees is kind of vaguely feels good. This is really obvious, yet we can't prove it. So it's like we're one step closer, but not quite there. So that's where we're going. So this geometric view was the topic of Dion Harmon's PhD thesis here at MIT, and it's also with John Iacono, Danielle Kane, who was an undergrad here, and Mihai Petrescu, who was an undergrad and a PhD here. It was published 3 years ago, 2009. So here's the idea. Access sequence, this is the sequence of searches you do. That's very easy. You just map it to the set of points where, I guess, I'm going to switch things on you. Sorry about that. X-axis is going to be space. Y-axis is going to be time. And I'm going to look at a specific example of this. Sort of pinwheel. There's 4 axes. At the first time, we access key 3, then we access key 1, then key 4, then key 2. Okay, we've been drawing this picture throughout the lecture. Now the interesting part is if you look at a binary search tree that actually accesses these elements, here's the exciting part. We're going to map this to a point set, which is which nodes get touched during a search, during each search. Okay, this is the fun part. So what does touched mean? I erased the model. But in general, with the binary search tree, we only have one pointer into the tree. It starts at the root. It can go left. It can go right. It can go to the parent. Every node that gets visited it can do rotations. Every node that gets visited by walking, that's what I call a touched node. Just look at all of them. So, for example, in this picture, get a color. Suppose maybe we're lucky and key 3 is at the root, so that's the only thing I touch. If that's the case, when I access 1, it's definitely not the root. So in particular, I definitely have to have touched that node. And I'm just going to fill in a reasonable choice. I happen to know this is a valid binary search tree. Not so obvious, but you can find one. I'm using here the greedy algorithm, actually. I'm cheating. We'll get to what that is. But in general, some point sets, like this point set, are not valid. There's no binary search tree that has this touch pattern. You just can't jump around, teleport without getting somewhere. But this one is valid. So which ones are valid? Oh, sorry, I need one more point. Let's do that. Which ones are valid? Which ones are invalid? How did I know that that was invalid and now this one is valid? Well, there's the theorem tell you. Then what I was just doing there will become clear. So I want to know when is the point set a valid BST execution. And I claim it is if and only if in every rectangle spanned by 2 points not on a common horizontal or vertical line.